Welcome to today's lesson. In this first tutorial, we will be able to convert from exponential to logarithmic form and evaluate logarithms. So we are in the first half of section 4.4 in our textbooks, and we're going to have some logarithmic fun, but I believe that what I meant to say was we're going to be talking about logarithmic functions. Okay, that's sure. Okay, that's hilarious. So the inverse of an exponential function is our logarithmic function, and that's what we're going to be exploring today. They are inverses of each other, the exponentials that we just learned how to graph and the logarithmic that we will learn how to graph later today. For x is greater than 0, so we must be talking about positive x values. For a greater than 0, so we must be talking about a base that is positive and not equal to 1, we have this logarithmic equation. Y is equal to the log base a of x if and only if our base a raised to our y exponent is equal to x. That is, first of all, how to convert from logarithmic to exponential form. So we have this logarithmic equation and we have this exponential equation, and they are identical except, well, one's in logarithmic form and the other one's in exponential form. But notice that the base is a here in the symbol and the base is a here. The x is just our number, I call that, and that's on the other side of the equal sign here. And on the other side of the equal sign here is our exponent, and that's where our exponent is here. How we read this symbol, just in case you have not worked much with logarithms, this symbol is read log base a of x. That's how I like to read this symbol, the log base a of x. And I also want to make sure that you're writing this symbol correctly, because if you notice, if you sort of draw a line through this entire equation, everything is in the same line except our base, which is a subscript. It's a little bit lower. So I'm going to go off here to our little printing paper. The L, the O, and the G are all on the same line. The X is on the same line. It's just that the A is a little bit lower. In fact, I make it drastically lower, kind of in the tail of the G right there. So I make sure that this is all in a nice line. I do not want people to write the log base A and then have this X sort of, floating up here. That's no good. I call this floating, and I don't like that. So please make sure that you're not doing that. The X is in line with the log of the log symbol. Okay, so a logarithm represents an exponent. That's why in logarithmic form, the logarithm is equal to the exponent. I see the exponent clearly over here because it's a superscript, but here it's equal to the exponent. So let's just pick an exponent of 2. I can write infinite logarithms that are equal to 2. Just depends on what base I want. The first one I'm going to choose is the log base 3 of 9. Now, why is this logarithm equal to 2? Well, because the base 3 would have to become squared to become 9. So that's one logarithm that's equal to 2. If I change my base, let's say that I change my base to a 4, well then obviously I have to change my number from a 9 to a 16, because 4 would now have to be squared to be 16. Let's write one more logarithm that's equal to 2. Maybe I choose base 5. If I choose base 5, then 5 is going to be squared to become 25. So the log base 5 of 25 would also be equal to 2. I challenge you to write at least one more logarithm with a different base than I've used that would also be equal to 2. I'll do that as a little try problem, and I can check that when I do your notes. So our first objective is just to be able to convert from exponential form to logarithmic and from logarithmic form to exponential. So I've got 5 examples here to do this. Let's do 2 to the 5th is equal to 32. We all know that this is true. If I convert out of exponential and into logarithmic, the first thing I would write down is the log. My base in this case is a 2. The number is 32, and that will be equal to my exponent, which is 5. The log base 2 of 32 is equal to 5. So that's my first conversion. Let's convert this exponential. This is 4 to the 1/2 power is equal to 2. I put this here to remind you that when you see fraction powers, that means it's a square root. In this case, or that means that it's a radical. In this case, it's a square root because it's a 1/2 power, and obviously the square root of 4 is equal to 2. So I wanted to remind you that radicals appear as fraction exponents. So I write the log, my base this time is a 4 of the number 2, and that would be equal to my exponent of 1/2. So we're just converting. We're just converting from one form to the other. That's why I'm doing a little double arrow. It was an if and only if statement, which meant that it's biconditional. It works both ways. These last three are in logarithmic form, so I need to convert out of logarithmic form and into exponential form. So the first thing I need to identify is what's the base? My base must be a 9, so I'm going to start with my 9. My exponent is on the other side of the equal sign, so that must be -2. So 9 to the -2 power, and the only other number that's left is the 1 over 81. Let's remind ourselves why this is actually true. A negative exponent means to take the reciprocal of our base, so it's going to be 1 over 9, but then the 2 is going to square it to 81, so 1 over 81. Let's convert our next one. This is also in logarithmic form. And I need to find my base, which my base is the 3, so I'm going to write that. And then the exponent must be a 2, because it's 3 squared, and that must be equal to w. Got to make sure that your parts are in the correct places now, because obviously there's no way of checking ourselves here, because we have a variable. We could solve for w now. We know that w is equal to 9. And of course I could do some nonsense like I did here, just to make sure that you know where all the little pieces are supposed to go. The base in this logarithmic equation must be this little box. And the exponent in this logarithmic equation is on the other side of the equal sign, which is heart. And of course, we all know that when you raise a box to a heart, you get an asterisk. So this is just a conversion page. We should be able to convert from one form to the other. Let's talk about some basic log properties. And I'm not talking about that they're brown or that you cut them in half or that they burn in the fireplace. No. We're talking about logarithmic properties. Okay, wow, 2 jokes in one day. So these are some of the basic log properties. You should just get to know these because you're going to see these every now and again. The log base A of 1. We should all know that this is equal to 0 every time because the base, any base, raised to the 0 power is the only way to get the 1. So we just know this. This is sort of like a sight property. When you see that, there you go. And if you need to convert, or not convert, look at it in terms of exponential form, I'll just choose a base of 7. 7 to the 0 is equal to 1, and we all know that that's a law of exponent. So our basic log property includes log base A of 1 is equal to 0. What if we have log base A of A? Again, this is representing an exponent because we see the log symbol. Which exponent? Well, A would have to be to the first power to get itself. And that makes sense because 7 to the first power would remain as a 7. Okay, another basic log property. Now let's say, what if we have log base A of A to the x? Again, it's representing an exponent. What does A have to be raised to get A to the x? Well, hopefully that makes sense that it would be x. It's sort of like the log base A and the base A kind of cancel each other out, and x is what's left. Or 7 to the x power would have to be equal to 7 to the x power. Okay, well, hopefully that makes sense. The next one, what if we have a base and we raise it to the log base A, sorry, we have base A here, and then it's log base A of m. What would that be equal to? This is a little bit tougher to see, but it is going to be equal to m. And it's sort of similar to this third one. The log base A kind of cancels out the exponential base A so that x remains. In this case, it's kind of backwards. The exponential base A cancels out with the log base A. They kind of cancel away, and you're left with m. Let's explain it like this. Let's take a base 7, and let's raise it to the log base 7 of 49. According to the property, the base 7 and the log base 7 would cancel away, and this would be equal to 49. Let's see why this is true. Let's look just at this exponent. This is the log base 7 of 49. Well, hopefully you know that the log base 7 of 49 is representing a 2, because 7 has to be squared to get 49. So if this is ultimately representing a 2, let me sort of put a big 2 through here, then we're talking about 7 squared. And of course 7 squared is 49. So it makes sense. The base 7 and the log base 7 cancel away, and 49 would be left. So that's why this is one of our basic log properties as well. And then our final basic log property, if we have the log base a of x, and that's equal to the log base a of y, well, as long as you have the same bases here, then you must know that x and y have to be the same. It's like the equality property for our logarithms. So those are our 5 basic properties. Please get to know those. Let's start evaluating. Evaluating has the word value in it. And when we're evaluating our logarithms, we're finding that value. Each one of these logarithms is equal to an exponent. All we need to do is find that exponent. Some people can just see them real fast. Some people might want to convert to exponential to figure it out. I need to know, what does 2 have to be raised to get 16? Now, some people might not know that, so they might just come over here and say, okay, well, the 2 to the x has to be equal to 16. That's the exponential version of this. So what does x have to be now? Maybe that's a little bit easier to see that, oh, we're equal to 4, and that is our value. 2 to the x, that means 2 to the 4th has to be 16. If we're looking at the next one, we need to know what 3 needs to be raised to get 1 over 27. Well, the first clue I can see is that I see a fraction, so we must be dealing with a negative exponent. And again, if you have trouble seeing it, just come and say 3 to the x is equal to 1 over 27. Maybe that helps you. Maybe some people convert the 1 over 27 to, let's see, 1 over 3 cubed. That's what 27 is. That helps. And then if I want to put it in terms of base 3, I'd have to make a negative exponent. And that makes sense that x is equal to negative 3. Again, I knew that something had to be negative, because if I have a base turning into a fraction, then it must be a negative exponent. And 3 being cubed makes the 27. So that makes sense that this is all equal to negative 3. This work is not necessarily needed, but if it's helpful, then please do so. Here's our last one. Log base 5 of the square root of 5. What exponent does 5 have to be raised to get the square root of 5? I feel like we just talked about that when we were converting, not there, but right here. Didn't we have a 1/2 power? And that was, I said that was equal to a radical. So now we've got a radical, and a radical means that we have a fraction power. If it's a square root, then you have a 1/2 power. If this were the cube root of 5, then it would be the 1/3 power. If this is the, I don't know, 7th root of 5, then it would be the 1/7 power. So when you see a radical, you know your exponent is a fraction. And in this case, it's equal to 1/2. 5 to the 1/2 is the square root of 5. Great. So let's talk about the 2 buttons that are on your calculator so that we could use those. Common logs versus natural logs. We all have 10 fingers. That's why our base for our digits, we have 10 digits, 0 through 9. So all of our numbers are using one of those 10 digits. Common logarithms mean that we're talking about base 10. So we don't actually write, because they're so common, we don't actually write the little base when the subscript is a 10. We actually just write log of x or log of whatever. When you don't see a subscript, it's implied that it's a 10. So each one of these is base 10. You don't see a little subscript, you don't see a little subscript, you don't see a little subscript. So if we wanted to evaluate these, we could use the button on the calculator for common logarithms. Hopefully you don't actually need the button for the first one. The log, base 10, of 10, of course, is equal to 1. That's one of our sight properties. If you wanted to plug in to the calculator 2, I have no idea what the log of 2.5 is, but 2 times the log of 2.5, make sure you close the parentheses that the calculator gives you, and give me an approximate, and that is approximately 0.796. Remember, we always go to 3 decimal places unless we're instructed to go farther than that. Okay, so when we type in the log of -2, you get an error. And if you look at I don't know why I just did that. That's fine. There doesn't make any sense. Remember, we said that the value for the input, the x value, had to be positive. That's part of the domain. We'll talk about that in the next tutorial. The domain has to be a positive input, so we don't have the log of -2. It doesn't make any sense. Our natural logs have a different base, and that's the base of e, that irrational number we talked about earlier. In fact, whenever you have the log base e, we definitely don't write the little e down here. We actually have a brand new symbol, and it's the natural log symbol. So whenever you see the ln, that's your natural log. You don't see the little base, but you know that e is the base of the natural log system. So it's a different button. It's underneath the log button on your calculator. So if we wanted to figure out what the natural log of e is, well, hopefully you don't need the calculator to figure that out. That's equal to 1. Basic log property. 5 times the natural log of 3, we would need our calculator for that. And that is 5.493. And for the same reason in part C of example 2, we had nothing null set. The natural log of -1 does not exist either. So that's a good beginning with our logarithms. Remember, the key is that logarithms represent exponents, and we'll practice with this in class. I'll see you then. Bye-bye.